reversible computing was born historically as a topic motivated by these connections between physics and computation. And the way I would like to frame it to you in this discussion is via this question: is KT log 2 fundamental? Well, if you look at a primitive gate like the AND gate we've spent so much attention on today, we have an x, y, and x and y, and the 4 possibilities. And it gives these outputs over here. And you know, if you stare at this output, you realize that this is irreversible. Every time you use an AND gate, you can't go backwards anymore. And that means if you had a random xy coming in, you have less randomness of the output. And so some entropy was charged to your credit card here. Maybe banks should always charge in units of entropy instead, if dollars. I know some of my kids would love that. But that loss of information means that an AND gate cannot but cost some energy every time it's used. But can we build a computation without using AND gates, without this kind of a cost? It turns out the answer is yes. And the way I can show you the answer is yes is really neat. And it is this answer which fascinated Richard Feynman and in many ways also got me started. And that is by showing that you can build a computer out of just billiard balls, pool table balls, knocking together and hitting each other. This is a mechanical model of computation. And yet it is so inspiring to look at this model because all it requires is the laws of Newtonian mechanics. It's frictionless. All the balls will roll around. And I will now show you how we can build logic gates out of balls moving around and colliding. Let's say we have a ball here, and it's going to shoot off in some direction. Another ball may or may not be present here. It will also shoot off in a direction. Let's call the absence or presence of this ball x, and the absence or presence of this ball y. Now, the two balls will collide because they have a finite radius at some point and subject to the accuracy of my drawing. And then they will bounce off and go to certain final positions. So this ball, if there were another ball here, would bounce off, come here. But if this ball had not been present, if y had been 0, this would have gone somewhere over here. Now, if both balls were present, we'd get a ball over here. If x were 0, this would have gone straight and ended up somewhere over here. And therefore, we now have a logical assignment for the output values. What is this one? Somebody tell me. Purple shirts are OK? How do I express the presence or absence of this top ball in terms of x and y? OK, you can do one. Anyone? Go ahead, purple shirt.
Oh, okay. So I would say, well, both balls have to be present, so 1, 1.
In terms of x and y?
Yeah. X, Y, sorry.
X, Y.
Yeah.
Exactly. OK. Fellow in the corner over there, what's the next ball over here? How do I represent this?
So the ball there happens, so it would be the ball, so y would go there, so it would be x bar y.
That's right, x bar y. And then this one, it follows this by symmetry x, y bar. And this one is the same as the top. It's x, y. Look at that. So I have a gate here. And I can make an AND gate because this is x and y. I can make a NOT gate by always having a ball y over here, and then it will select this line will be x bar because y will always be equal to 1. So I have an AND gate and I have a NOT gate, and I get all computation just by having balls collide. So this is a famous result. I encourage you to read more about this and its models. Fredkin and Toffoli wrote about this in a paper called Conservative Logic in the International Journal of Theoretical Physics. No computer scientists here. In 1982, volume 21, page 219. Okay. There's much more with regard to this, and I'm not going to go into that in detail for lack of time, but I want to now share with you a little more of their story and how they then built a language of gates, reversible circuits, and reversible computation. And that's where we'll end in 10 minutes. By the way, I can't resist but tell you a little bit about this fellow. So Ed Fredkin is, to my knowledge, the only person who's become a faculty member at MIT with no graduate degree, no PhD, no bachelor's degree, and no high school degree. And he owns or owned an island in the Caribbean. Who knows where it is these days or if it exists anymore for many reasons. But he's quite a character. And he got started by working not just on this, but ideas with cellular automata. And I think he gave a talk at the Center for Theoretical Physics just 2 or 3 years ago. A very creative individual. And one of the things he's known for is a family of gates. And I want to introduce to you now such a family of reversible gates. Oh, by the way, also, I know nobody who's actually built a physical billiard ball computer. If you're an aspiring Europe, why not? Because maybe you could build one that operates with very little energy. Why doesn't Intel build its computers out of balls inside processors banging around? Anyone know? Speed might be an issue? No. So that's not quite the reason. You know, practically speaking, you're probably right, but not from a fundamental principles standpoint. Yes, please.
Like space or crossover?
Space or crossover. So there is a way to cross over. If I have these things which are hard walls that are known as barriers, I can have X and Y come in, and you can stare at this and convince yourself that X and Y bouncing, they'll bounce here, they'll go off, bounce, bounce, bounce off of each other again, and always go like this. So for X and Y in, you get Y and X out. Works great. Not for Intel. Yes, please.
You mean it's small enough and quantum tunneling becomes an issue?
If it's small enough, quantum tunneling becomes an issue. You're too smart for this question. The answer is no, not that. But an expert might say that. Others? Yes, please.
I guess it's really hard to find material that has like fully elastic properties.
It's very hard to find a material that has the right kind of elastic properties. Actually, you want these to be inelastic as much as possible.
I mean inelastic.
Oh, good. Hard to find an inelastic hard sphere model material. Well, there are some very hard materials. I bet if you're an undergraduate at MIT, you could solve that problem.
Is it difficult to do fan out?
No, it's actually very easy to do fan out, but I haven't shown it quite here. Actually, you can turn this gate into a fan out if you think about it for a moment. Yes, please.
It's hard to reset after you've used it.
It's hard to reset after you've used it. You're almost getting the idea I'm looking for. And this is the thing, the crux of the issue. If you have a small error, a small misalignment, a small mistiming of a ball that went a little too fast or started a little too late, then you have to correct for that error. because otherwise the error will just cascade and grow into bigger and bigger errors. And pretty soon the balls will all be moving chaotically all over the place. It turns out the only reason you need to plug your computer into the wall is because you need your computer to be reliable, to kind of always put up the blue screen of death at exactly the same time. Because otherwise, at least from a fundamental principle standpoint, you do not need to consume energy for computation. And that's the main point I want you to gather in the last 5 minutes of the lecture. Question?
Me or,
Yes.
So is this true for all reversible gates?
This tolerance,
This sort of tolerance problem.
this susceptibility to errors. Yes and no. But I'd like to come back to that when we talk about error correction. Okay.